Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. I'm happy to announce that the new Physicawesome Instagram account has been officially opened. Follow Instagram better than YouTube because there's been some trouble with the YouTube notifications, and therefore Instagram will probably be more reliable. Today we will introduce momentum. First, we will see how it works in Newton's second law of motion, and we will express it in terms of this new quantity. Then, we will see that impulse is a quantity that's pretty correlated with momentum, and we will introduce it too. And finally, we will explain how momentum is conserved in collisions. So, let's start! Alright, let's introduce momentum. Imagine you have a mass in space, and this mass is moving with velocity, this is mass m, and it is moving with velocity b. We define momentum, that is a vectorial quantity, p. It's defined as the mass times the velocity of an object. This quantity proves to be much more useful than velocity in itself, because, for example, it gives you an idea of the quantity of movement. Let's see, if you have a very big object that is moving slowly, it's obvious that it's carrying lots and lots of movement with it, because it has to move a lot of particles in that sense, a lot of mass. On the other case, if you have a small object that is moving at the same velocity, you have the appearance that it's moving and it has lots of less movement, lots of less momentum, because that object doesn't have to move that many particles, that much mass to move with that velocity. So it will be a very useful quantity for us as physicists. Now let's see how it works and how it relates to Newton's second law. If you recall, Newton's second law is F equals ma. And we know that A, from our previous video, you can see over here that A equals dB dt. But now we see that if the mass is time independent, we can take it from here and put it inside of the differential. And this is ddt of mass times velocity. And what is this? This is momentum. So we can redefine Newton's second law and also extend it as ddt of p, the time derivative of momentum. And this will be very useful when our mass is time dependent, because in those cases our old formula wouldn't work. Great, now let's introduce impulse. In physics, we think of impulse as the sum of the force applied to the object at multiple times. That is, the force being applied at time 1 times a small interval 1 plus the force being applied at 2 times a small interval delta 2, delta t2, etc, etc, etc. That is the force, the continuous force that is being applied times the time that force is being applied. Therefore, we find in a more general form that applies to more situations, impulse I as the integral from t1 to t2, that is the impulse that has happened between these two times, of the force times the t, and this is a vectorial quantity. That is, for every little dt of time, every little time element, we have a force, and then we sum all of those up. Recall from earlier that we found that this is t1 to t2 dt, and force is no other thing than the derivative of momentum with respect to time. And we can cancel these different differentials, and we get that this is dp. We can easily solve that integral, and it's p at t2 minus p at t1, and this is just delta p. So we see that impulse and momentum are really correlated, as impulse is just a change in momentum. For every physical quantity that we introduce, it's useful to see what its units are. In SI units, we can see that momentum and impulse have the same units, and we can get them from two different expressions. The first one is this one, and as we see, the units of momentum are the units of mass, that is kilograms, times the units of velocity, which is meters per second. Another way to get those units is from the definition of impulse, because we know it has the same units. Therefore, we see that this is the units of impulse, which equals the units of momentum, are the units of force, which is newtons, times the units of this differential, which is time, that is seconds. So these two expressions are equivalent, and we can see that if we substitute the definition of a newton, that is kilograms meters over second square, times seconds, we get 2 seconds that cancel, and that expression over there. So we have two different ways in which we can express the units of momentum or impulse. Great, now let's explore the implications of these quantities for our collisions. We have a time t prime. Right before the collision has happened, we have these two objects going against each other, and then after a small time interval later, a really small time interval, we have the two objects going in opposite directions. So we remember that F, that is the force that these two objects can feel, that the whole system can feel, equals dp dt. For a more detailed discussion of momentums of systems of particles, you will need to wait for next week's video. We know that this is the force our system feels. However, as we're going to take this small time interval, we're going to assume that it is so small that no force has time, no friction, no air resistance, no gravity has time to affect our system. And the collision happens in an instant. Therefore, we will say this is going to be 0. And we will assume that our momentum is going to be conserved. Therefore, we're going to define our I hat vector over here and over here. And we can see that the initial momentum, that is P of the system initial, equals m1 times b initial 1 in the I hat direction plus, well, minus, because it's pointing opposite to our unit vector, m2 bi, 2 in the I hat direction once again. And now we have our final momentum, the P final of our system, which is minus m1, because it's pointing in that direction, bf1 in the I hat direction, and plus m2 times bf2 in the I hat direction. Now, as we have said that our momentum is going to keep constant through time, we can equate these two momentums and we get that, and let me drop the vectors as everything is multiplied by the same unit vector. We get m1 bi1 minus m2 bi2 equals minus m1 bf1 plus m2 bf2. So we see we have in this equation two quantities that should be given to us, as they are the initial conditions of the problem, and the masses, we already know them, and therefore we have two unknowns, that is the final velocity of object 1 and the final velocity of object 2. Therefore, we are not ready to solve this system. To do so, you will need to wait to our energy videos, in which we will use another conservation principle, that is energy conservation, specifically kinetic energy conservation, to solve these systems of collisions. But from now on, you know that momentum has to be conserved, and you can get one of the two equations that will determine your solution. That is all for today. Today's video was a little bit short, but I hope you liked it and also that you understood these concepts, because they will play a central role in lots of our discussions about classical mechanics. I'm happy to announce that soon after this video is released, in 2 or 3 weeks' time, we will start a new electricity and magnetism series that will alternate with our classical mechanics series. I hope you liked this video, and remember to like the video. If it was the case, press the subscribe button and the bell so that you don't miss any of the new videos, and see you another day with more Physicawesome!